introduction. And actually it's very important to our president that things are always pronounced in German, so you did a good job. So I also wanted, before starting, to really thank the organizer and Jeff for inviting me. I'm very happy to be here. I think this is a wonderful opportunity to interact with people. I learned a lot, and I learned also very special things. For example, I think Carlo told me that there are fake Italians, and that I'm one. So I didn't know that before. I knew that there were fake Jews, but also fake Italians. So I'm going to talk about, of course, about quantum mechanics, as you can see from the title. I'm in kind of a quantum information series, and therefore the approach I'm taking towards understanding quantum mechanics is largely influenced by information theory. And so, what do I mean by information theory? I have just one slide which explains the kind of main concept that I'm going to use. And, you know, information theory is largely about things that someone knows something. For example, here we have Alice knowing the outcome of a measurement result. So this probably indicates what she knows. She has read it here, that it was an outcome plus 1/2. And maybe another party who doesn't know have that knowledge. And now in information theory we develop schemes which allow them to exchange knowledge. So for example, Alice could encode the result of her measurement into bits, send them to Bob, and Bob could decode that, so that he ends up having the knowledge that Alice has. So that's something that is studied traditionally in information theory. Now what I'm going to do today is just use information theory as an inspiration to kind of have another perspective on quantum mechanics. And maybe I should say that the outcome of this project was a very different one from the one I expected. So the outcome at the end is that I'm completely puzzled and don't know how to think about quantum mechanics any longer. I will just essentially present the kind of thought experiment, and the thought experiment I will not try to direct you towards any particular interpretation, because it's kind of, I don't even know how to fit this thought experiment with any of the interpretations really. So that's probably going to be part of the discussions. So first, I would like to start with something that I regard as an information theoretic thought experiment. Of course, you're probably used to physics thought experiments, but what I'm going to present to you here is just something you may already know, which is the muddy children paradox, or muddy children problem, in a reformulation suggested by Lydia Del Rio. So what is this thing? For those who know it, they will immediately recognize what it's about. So you assume that there's an island with people on the island. Some of them have, you cannot see it from the back, but actually I can tell you this. A has blue eyes, B has also blue eyes, and C has green eyes. And this is important because one day a traveler arrives, T, and let's say it's Sunday, and then upon his arrival, the inhabitants of the island tell him that there's a special rule. And this rule is that anyone who knows that she has blue eyes must leave the island on the next day. That's just the rule on this island. I don't know where it comes from, but that's the rule. And obviously they are still there, so probably they don't know their own eye colors, and they are nice to each other, they don't tell them and so on. But now this traveler is a bit surprised and answers, this is strange because I see people here with blue eyes. So what happens? On Monday, no one leaves the island. Then he stays for another night, and on Tuesday, A and B, these were the two women with blue eyes, left the island. So what happened? Let's just briefly go back. So, as I said, the traveler arrives on Sunday. Then he actually, and this is in some way the puzzling thing, he says something that everyone on the island apparently already knows. Because everyone sees at least one person with blue eyes. This person now essentially just confirms that. He says, I see someone with blue eyes. What happens now? B, let's look at the reasoning of B. B, of course, sees that A has blue eyes. So she thinks this is perfectly consistent. In particular, I cannot conclude from this information I got that I have myself blue eyes. I may have or may not, but because A already has blue eyes, both variants would be consistent with the information of the traveler. So, accordingly, B doesn't leave the island because she cannot conclude she has blue eyes. However, on this, A can now, let's now take the perspective of A. A now observes on Monday that B doesn't leave the island. So, what does A conclude? A must conclude that B knows that she has blue eyes. Why that? Because the only possibility why B didn't leave the island was that she sees someone else with blue eyes. And because A knows that she doesn't have blue eyes, it can only be her. So A knows on Monday that B knows that she has blue eyes, and she concludes from that she actually has blue eyes and will leave the island on Tuesday. And of course the situation is symmetric for B, so A and B leave the island on Tuesday. Okay, I don't want to spend too much time with this example, I just want to point out one important thing. So as I said before, the information given by the traveler was something that apparently everyone already knew. There was nothing, everyone knew that there's someone with blue eyes. However, the important thing, and this will be the point, kind of the starting point of the quantum information sorter experiment that I'm going to tell you about, is that because the traveler makes this statement, A, for example, learns from that B now also knows that there are people with blue eyes. And this was maybe a priori not clear, because A doesn't know whether she has blue eyes or not. So if she had green eyes, then it could have been that B doesn't know whether there are people with blue eyes on the island. So the information is actually useful because the information says something, tells A something about the knowledge that someone else has. So it's information about the knowledge of someone else. So that's essentially the conclusion that A can draw only because this person is here and apparently makes a statement which is useless. Okay, so this is probably an example that many of you already knew, but the important point I want to make is that for certain arguments it's just crucial to know what others know. Otherwise we simply cannot arrive at the same conclusions. And actually this is even in the let me just very briefly come back to information theory. If you have a communication scenario, I drew this picture. This is, however, maybe a slightly too naive picture, because what's actually going on is that what Bob knows from that is that just Alice knows that Z was 1/2. And usually we make from that a conclusion and say, if I know that my partner, and I mean, this is not about trust, so let's assume everyone trusts each other. So if B knows that A knows that the outcome of a measurement was +1/2, then usually, naturally, B would conclude that the measurement was +1/2. And what I now would like to do is to study physical theories, in particular quantum theory, based on, or with regards to this kind of consistency requirement. So what do I mean by that? So in the following, when I say that a theory, or I will actually only talk about quantum mechanics, except for one very small example, and when I say that the theory is self-consistent, what I mean by that is the following, that if, B, let's say B uses a physical theory, and within this physical theory, he models Alice, and concludes that if Alice also uses the physical theory, she would come to a particular conclusion, for example, that a certain measurement outcome is +1/2. Then B may conclude, this is now an assumption that this is possible, and if this is true, I say it's self-consistent, that B would then say, now actually I concluded that this value is +1/2. And usually we are not maybe doing that too explicitly, at least in physics. Maybe the philosophers are probably much more careful, but in physics we usually do that. So for example, if I have a situation of two particles which fly around, and this is now the only example outside of quantum mechanics, A may just say, what was if I was an observer that would have that has the same velocity as the particle here? And then A would kind of reason about that and come to the conclusion that that particular observer B would come to the conclusion, let's say, that these particles collide, for example. And then from the fact that A concluded that another observer would see the particles colliding, she would conclude that the particles are actually going to collide. So you reason via taking the perspective of someone else. This is just an example. The quantum mechanical ones will be slightly different, but this is just to illustrate the idea. So the main question that I would like to ask, that I wanted to ask when I was designing this kind of example, this thought experiment that I'm going to explain to you or to show to you, it was this question. Does our quantum world allow consistent reasoning in that sense? Now I have to make an assumption, because if I'm talking about quantum mechanics, we may understand different things. And I just want to be clear from now on what I'm going to say I will make the assumption that quantum mechanics is kind of a universally valid theory, at least to the extent that also large objects that could themselves be observers could in principle be modeled with a quantum theory. Now, I don't want to impose that or say that this assumption is necessarily true. Actually, if you think it's not true, what I'm going to tell you then can be seen even as a confirmation that it's maybe a bad idea to assume that. So I will make assumptions which will at the end contradict themselves, which means one of the assumptions was a bad one. But let me now for the moment make this assumption. I will be a bit more precise just in a moment about what I mean. But essentially it's the assumption which is illustrated by Schrödinger's cat. So I will assume for the moment that if a cat is in a perfectly isolated box, then a correct quantum mechanical description is that the cat is really in a superposition, and I could in principle do measurements in a superposition basis and would retrieve and would be consistent with quantum mechanics in all predictions I'm making when I measure now this cat in superposition basis. Now, by the way, this is the most real Schrödinger cat I could find, and it's just outside of my house. So you know, what you see in the background is actually the house where Schrödinger lived when he was in Zurich. And they put this cat here, which is a metal cat, which however has the nice property that depending on the light conditions, it either appears dead or alive. So if you're next time in Zurich, I can recommend that as a slight excursion to this street, which is indicated here. Okay, so what do I mean by the universality? So I'm not trying to claim now that there is no classical world. I'm just essentially taking a kind of Copenhagen picture. I want to be very kind of general. So what I'm assuming essentially is just that the split between the quantum system and the measurement device can be shifted. That's what I mean by the universality. So it shouldn't matter whether we describe a system just as the small quantum system and everything around is modeled as a measurement device, or whether we, for example, say, let's also model the measurement device as part of the quantum system and only the observer as a classical system, and the observer could even be, as long as I have an outside observer, I could even include other observers as part of the description of the system. I just then, of course, can only talk about the outcomes this person sees and not about these outcomes, because this cat is now part of the quantum system. But what the claim is that if I'm, for example, calculating the probability of the outcome of a particular measurement, then for this person here, what probability does he have when observing, for example, spin down? It will be the same independently of where this cut is put, as long as the calculations are done correctly. That's essentially, this was just Bell's idea. It shouldn't even depend whether this person has a PhD or not. So that's essentially the statement that Heisenberg always pointed out, that of course there are some restrictions to that. The cut should not be beyond the observer, and it cannot be too close to the quantum system, because I need to take into account the effects I really want to describe. So if I prepare a spin in a superposition, I cannot regard this as a classical system. That's probably obvious. Okay, so this was just a preparation. Let me now come to this actual thought experiment. The thought experiment is may at first place look complicated, but I will actually completely separate it into very simple parts, because it involves essentially 4 different agents who reason about the knowledge of the other agents. So in the same way as before, as we had these in this classical experiment, where people are on an island and think about what another, so if one may reason about the knowledge of F2 and so on, they reason about each other's knowledge. So F1 and F2 are called like that because they will take a similar position as Wigner's friends in the Wigner's friend experiment. That's why they're called F1 and F2, and W is Wigner, and A is an extra person. You may think of him as the assistant of Wigner or whatever. So let me now continue. And before I describe the experiment, I should point out that it's in some way so the experiment is based on ideas coming from many other kind of thought experiments that have been proposed in the literature. In particular, Bell's experiment, then an experiment by Czaslaw Bruckner, an extension of the Wigner's friend experiment by Deutsch, and an idea by Hardy. This is all goes into this thing. Now, the description will be mostly in pictures, and just to be sure that the pictures are well understood, I have here this notation slide, and this would just should depict the spin-up state, and this is the corresponding measurement outcome set plus 1/2 that I would then obtain with certainty if I have such a state. And the same here for spin down, which gives me minus 1/2. Okay, now we can start, but the starting point is essentially just the usual Wigner's friend experiment. So I have the friend, here it's F2, it's one of these two women that you saw on the previous slides, in a perfectly isolated lab and equipped with a measurement device. And now we assume I assume, by the way, that the lab will for a moment be open so that I can inject the spin particle. This will be important because it shouldn't be already in the lab for some reasons. And the convention here is that this is just a superposition with a positive sign in between of up and down. Now F2 is supposed to measure that in the up-down basis, and we'll see an outcome, probably. Let's say plus 1/2, could also be minus 1/2. And of course, she reads this outcome and now knows that the outcome is plus 1/2. Now we can, of course, have a look at what is the description of this experiment from an outside viewpoint. So what would Wigner, who is outside of this isolated lab, describe the situation? He would just say, oh, the initial particle was in a superposition between up and down. I omitted here the prefactor of the 1/square root of 2. And so therefore, because the lab is perfectly isolated and because I assumed that there is no collapse, I assumed this universality of quantum theory, we will have a situation where we have this superposition. I mean, that's the standard argument of how people think about measurements if there's no collapse. And as I said, this is for the moment just an assumption among many, and one of them will be wrong. So if you don't believe in this assumption, that's fine. But that's for the moment the assumption. So this is now just an example of the Heisenberg cut, so to speak. You can now say Wigner put the cut at a different position from F2. Wigner put the cut outside of the lab, and of course if you look from outside of the lab, this is just the correct description of this big quantum system. And there's also no inconsistency, because if Wigner now measured whether it was up and down by opening the lab, he would just obtain again the result that with probability 1/2 he would see up, and with probability 1/2 see spin down, and of course what he sees would coincide with what F2 would tell him. Now, clearly, I mean, this is just to illustrate, F2 is just another observer who put the cut somewhere else. For her, it wouldn't make sense to put the cut here, because then she cannot talk about outcomes that she observes, so she is forced to put the cut somewhere here. So, again, just to stress that point, there is no problem here, at least not one that I want to point to, in the sense that this just is perfect. So the Wigner's friend example is perfectly consistent with the fact that we can move the quantum classical cut. So if we can move it, then there is no contradiction. I take now the Wigner's experiment, the one I described as a starting point. And now I'm going to describe a few steps. And similar to Lydia, I would also appreciate questions if something technical is unclear. It will not be too technical, but it's important that you ask if a step is maybe unclearly described and you don't know what happened. So for the moment, I just have this situation that I inject this particle, it's measured, and there is a person outside waiting. Now I introduce the first extension, and this is exactly the extension that David Deutsch, for example, already considered. He asked the question, so let's suppose that Wigner believes in a collapse model, and he would try to kind of falsify the fact that this lab is in a superposition. So, of course, in some way he could ask an experimenter to try to measure this in a superposition basis. And if the superposition measurement would come out in this particular way, then Wigner would conclude that his falsification failed. So I do that in the following way. I assume that there's this measurement basis. So this is a measurement basis for a measurement applied to the entire lab. It just means you either measure with a plus sign or with a minus phase. Of course, that's not a feasible measurement in practice, but importantly, there's nothing in quantum theory that tells us that such a measurement could not exist. And there's no fundamental principle that speaks against it, except if you introduce some collapse, which may be the solution to the arising paradox. So for the moment, we assume we can do this measurement, and we call this particular measurement, which is actually the one you would expect to be the outcome, as failed, because in that case, Wigner would fail to falsify the fact that there is a superposition. So what quantum theory really tells us is that if quantum mechanics is really universal, we know with certainty that if the particle is like that, and this was defined as the state with a plus sign in between, then the outcome here will with certainty be an outcome fail, and this outcome OK will not occur. That's just, I think, basic quantum theory applied to a weird situation. Now I introduce an additional extension. There will only be 3 extensions, so we are already halfway in the description of the experiment. So the second extension is that now instead of always letting F2 measure this spin right particle, she now gets a particle prepared by another person, whom I call F1. So F1 prepares a particle based on a random coin flip. And now to be a bit more precise, let's assume this is actually a quantum random number generator. I drew here a classical coin, but let's assume this is again a perfectly isolated lab, and from outside point of view there is no randomness. It's just some superposition state in a random number generator that is measured by F1. F1 sees this outcome, which can be either tail or head, and depending on this outcome, she will either prepare this state or that state. So one of these states is the one we've already seen before, and we know what's going to happen. And I will just here remind you of that and write it as an implication. So this is nothing new from what I've told you before. I just now combine it with the fact that we only prepare this state if R is tail. So in other words, what F1 now knows, or the conclusion that would be a correct conclusion from her, is that whenever I saw tail and follow this preparation procedure, at the very end of the day, this outcome by Wigner will be fail. And we will have 3 such implications. I number them here. So I will remind you of them, but this is just the first of them. So we know whenever there's tail, there will be this outcome fail. So in other words, in one case, in this case, F1 can perfectly predict what the outcome of W will be. There's nothing, this is not surprising, but let me also stress that in the other case, she cannot perfectly predict it, because if she prepared this state, then in this basis where W measures, both outcomes are equally likely. So in this case, she cannot make a prediction. But in the case where R is tail, she can make a prediction with certainty. And I drew the prediction here as a sort. So this is what F1 knows, so to speak. She knows if R is tail that W will see fail. Now we can say something more here. Let's now ask, now we kind of look at another perspective. Let's now ask what F2 can say. F2, let's suppose F2 saw Z plus 1/2. So then, and we assume everyone knows kind of the general scheme. So F knows the receipt. She doesn't know the value R, but she knows that F1 will prepare things according to that rule here that I've written here. So if she sees plus 1/2, she can certainly be sure. Yes, sir?
This rules
Yes, so this is, thanks for the question. So I assume that everything F1 does is in a perfectly isolated lab. So if F1 is now regarded from the outside, so if Wigner describes, let's say if Wigner describes what's going on in this lab, all that Alice does will be done in a superposition from his perspective. So that's important. For F1, it's just normal. I mean, she would just follow the rule as we do and describe it in the usual way as I would if I did follow the rule. But for Wigner, Wigner takes this outside perspective, and because this is a random number generator, so this is a superposition state at the beginning. Yes, so this will be a superposition state that is measured. Yes, yes, so the whole lab will now, so from Wigner's perspective, this entire lab will be in a superposition where one state is that R was tail and this knowledge is fail and so on, and the other state corresponds to that thing. I'm sorry. Okay. Oh, I hope you heard at least something of what I said before. Okay, I'll try to keep it here. Okay, then I can speak much more about it. Okay, we have now, we are now at this question, what can, I hope I clarified your question. Yeah. Okay. Now I want to take F2's perspective, and F2 could kind of ask, what does we could ask, what does F2 know? Now F2 could kind of be asked to make a prediction. What if she went and asked F1, what did you prepare? And she would see, if the outcome here is plus 1/2, then clearly it cannot have been that particular state that was prepared, because that would with certainty have given an outcome of minus 1/2. So F2 can conclude from the fact that she saw here plus 1/2 that it must have been this state, and therefore that F1 would have seen tail. So in other words, and this could even be verified experimentally, that would be very easy, you don't need the isolated lab. F2 could go to F1 and ask her, whenever she saw Z is plus 1/2, what was your R? And the answer will always be R equal tail, whenever this here happens. So I will also write that down as a rule. And it's kind of rather trivial rule from a quantum mechanics perspective. So the only thing I used here is that this preparation will never give this outcome. That's the only thing I wrote here. And now, of course, we could, just as an outlook, and I will make that more precise, already now ask what can F2 conclude from that. So let's say F2 now knows by this rule that R was tail, and now she could in principle say, if R is tail, then I know that whenever F1, so R equal tail, then she knows that W is fail. So in other words, F2 now knows that F1 knows that W will be fail. And I will just summarize that, because in principle I would have these nested things, but I will write it shorthand here. But it should really mean F2 knows that F1 knows that W is fail. This is just a logical conclusion that can now be drawn from that. And now we are already at the last extension of the experiment. I will now assume, and that's the reason why I put this party also into an isolated box. I will assume that there is this fourth person, the assistant, who can apply a measurement on this box. And now I don't want to kind of take too long for a technical argument, so I will now just make a claim that can, in the same way as the claims before, be directly verified in a very simple manner. So the claim is that if this lab is also measured in a superposition basis, actually the analogous basis to the one I defined here. So the basis where you have the outcome, let's say tail plus head, and then the other basis is tail minus head. And I also call these bases okay and fail. Then we can get an outcome which is okay or fail. And the claim which I'm now making without doing the calculation, but I can, if you like, we can do that in the discussion. It's a very simple calculation, analogous to the one before. We would just see that whenever this outcome is okay, then it must be that this outcome is plus 1/2. I mean, you essentially just write down the joint state of the two and then look at the state conditioned on this outcome, and you see that the state of this lab conditioned on the outcome okay is always plus, is always spin up, so therefore it must be this outcome. So that's the third rule, and I could now continue this argument and say, now of course, if he knows that, then he knows also that this must be true and so on. So I will just make that more precise now. But essentially, what I would like you to know now is following that, we have now derived three kind of conditions, which are deterministic implications. They're just implications which are valid for these three parties. So one for F1, one for F2, and one for A. And the one for A I didn't show, but the one for F1 and F2 I've shown in detail. Now suppose that indeed this outcome x okay occurs here. And I will argue later that this will actually sometimes happen. So suppose now that this person here got an outcome okay. And suppose that this person now announces this outcome to W. What can we now conclude? So W, this is now like this communication scenario. W now knows that A knows that Z is plus 1/2, because we had this was an implication that we have seen before. We know that whenever x is okay, so that's A's reasoning, that's important. So every reasoning is relative to an observer. So everything is relative. So A's reasoning is that whenever I've seen okay, then I know Z must have been plus 1/2. But because this x was told to W now knows that A knows that Z is plus 1/2. So I'm now careful not to collapsing these statements. I'm just doing logical implications. I'm not saying this means that W knows that Z is plus 1/2. Now I can continue with the next step. This is the step that we have seen before, that whenever Z is plus 1/2, then F2 knows that R must have been tailed. So we can add that to the statement. So W now knows that A knows, that F2 knows, that R, this coin, must have been tailed. And now we add the first one we derived, which is that we knew that whenever R is tailed, then W will be failed. So by the way, one point I should say for clarification is that these statements that W equal fail always are statements which are only true at the specific time. So this statement should more precisely read the outcome W at the time when this measurement is carried out will be failed. This is R equal tail means R is tail at the time when this outcome was observed. So I could in principle everywhere add times. So now we have this very long chain, and if I now did the thing, and this now connects to the beginning of my talk, if I now had a theory which would be consistent exactly in that sense that if I know that someone else knows something, I can promote that to my own knowledge, then W could of course conclude that he, when he makes the measurement, will see W equal failure. So this outcome of W I call also W. So W can, in this situation where A told him that x is okay, conclude under the self-consistency assumption that he will measure the outcome failure. So far it's just an analysis, and now the important thing is now the following. Let's now suppose we repeat this whole experiment many times. Each time these two parties will see something else, but one can calculate that the probability that both of them see the outcome okay is strictly positive, namely it's 1/12. So if we repeat this whole entire experiment from scratch again and again, there will at some point be a situation where W sees okay, and he's told by the assistant that X was also okay. And now you see that we are entering into trouble, because what we did before is to say that purely from the quantum mechanical analysis, where we just use the viewpoints of the individual parties, we concluded that this chain of things of statements is true. That he saw okay, but he also knows that A knows, that F2 knows, that F1 knows, that W must have been failed. Now, if the consistency assumption is taken for granted, we can conclude that. And now we are not quite at the contradiction, but if we now assume that everyone who sees an outcome only sees that outcome and not something else, I call that the single verb assumption, then this really means that the outcome W wasn't okay, but actually W has seen okay. So now we arrived at the contradiction. So in other words, W, from what he is told by A, must have concluded that he has seen the opposite of what he has actually seen. Okay, so that's already the whole experiment. Now I can maybe just summarize it in a slightly different way, just to make, again, kind of review what we have used. So you could somehow say this is like a no-go theorem. So we have made certain assumptions, of course. I've used certain assumptions to make this analysis. And obviously, because I arrived at the contradiction, one of the assumptions cannot be true. So that's, I'm now coming back to the starting point. So something so I'm not claiming that these are good assumptions. Actually, the opposite. One of the assumptions must necessarily be wrong. So what were the assumptions? One assumption I've made is that if I'm an agent in the world, I can use quantum theory to describe everything around me. In particular, I can, for example, describe Lydia as a quantum system, if I want. And so there's no rule in quantum mechanics that prevents me from doing that. That's an assumption I've made. Then the other assumption I've made is this promotion of knowledge, that if I know that someone else knows something, let's say, if not, I know that Czaslaw knows that it's now beautiful weather in Vienna, then I know that as well. I mean, again, this is not about trust. Or even if, it could even be stronger, if I know that if I was Czaslaw, I knew that the weather was good in Vienna, then I conclude from that it's good weather, the weather is good or it's sunny in Vienna. So that's, again, an assumption. So just to stress that, that's not something I take for granted, it's an assumption which I used. And the last assumption was that we only see one outcome. So if I observe an outcome 0, then I'm sure there's not also a copy of me that observes outcome 1, because otherwise there's also no contradiction. If I see 0, and I conclude that I've also seen 1, but I accept that there are copies of me that see different outcomes, like in many worlds, then there's not contradiction. But the theorem says one of these assumptions must be wrong. So let's briefly go through the assumptions again. So what yes?
You gave just this pattern as observability of multiple A.
Yes.
First time I used that wrong, since that's impossible, because there are 4 total states, one is the plus of the minus. So how can I how can you get false?
So this here.
And that can be.
So you're asking why this can be true?
Yeah.
Yeah.
What am I seeing wrong?
Okay. Aha. So, okay, maybe I could show the calculation, but there's one thing I actually didn't say that may be the source of the confusion. I omitted one technical detail. The technical detail is that in this coin here, I didn't, this is important for this particular calculation, I didn't assume that the coin is half coin, but I assume that the coin is such that the outcome tail occurs with probability 2/3, and the outcome head appears with probability 1/3. So it's a slightly unfair coin that I'm assuming that this is. And now if you can just write down the joint quantum state of this whole system, so of this lab and of this lab, and project onto the corresponding measurement basis, and then the outcome is 1/12. I mean, the amplitude is square root of 1/12.
So this is basically like the Hardy state.
Yeah. Yes, that's why I said there's this idea of Hardy coming in. Yes, it's one. I mean, Hardy has a whole family of states. Right. This is one particular Hardy state, so to speak. I mean, if you look at, of course, it depends on which perspective you take, but from the perspective of that you need to take in order to make this calculation, it is the Hardy state. That's right. Yes. So what I mean, so I just, okay, this measurement basis I've specified explicitly. So this was the one where we have just this superposition between, let me quickly, it was later I think. So there are 2 measurements on separate labs. And
Can you tell us what basis the system?
Let me briefly. Yeah, so the basis that I used for this measurement here, so this was the measurement basis for the measurement leading to doubling. Now I didn't explicitly specify the basis leading to the outcome X, but it's essentially the same basis where you here would replace, I mean, of course, it's instead of F2, it's F1, so it looks exactly the same. And here it's, of course, the outcome is the outcome of the coin toss, so this will be an R. So it's that R is head plus that R is tail, and then the other basis is that R is head minus that R is tail. So there are two different systems with two different bases. Maybe it's confusing that I call them, I use the same names for them, but they're on two different systems. Does it? Okay. So you have.
Did you tell us what basis the system is measuring in?
Yes. So now I just I didn't write it, but it's exactly it's this basis, except that here is an R and here would be an R. So it's essentially the same superposition basis applied to the R value instead of this.
Renato, you're running short of time, so.
Yes. No, but I will soon be. It's fine. I will do it in. I think I have 5 minutes left.
No more than that.
Oh, okay. Yes, that's more than enough. Unless there are. But the big question can then come at the end. So let's discuss that. So I just want to say what are possible ways out. The obvious ways out are, I mean, I said one could give up the self-consistency that was on the previous slide. Now we can discuss whether one wants that or not. Clearly, this makes clear what this assumption means. One way to give up another assumption I needed, I said that already, is essentially to call to many words. However, one needs, in order to really avoid this contradiction, one needs to go to an actually very severe form of many words, namely one where branches don't persist in time. This is important. So it would be very consequent many words, an interpretation where there's no connection between me now and me 1 second later. So I shouldn't think of branches which persist. So this picture would actually not be a good reflection of what would be needed to give up then. Then, of course, one could give up the universality of quantum theory in some way. And I mean, I also don't want to discuss that further, but that, of course, relates to the assumption that I told before, that large systems can be in superposition. I just want to make a side remark, which I find important, because people always talk about building quantum computers, and for me, building a quantum computer is a very fundamental an experiment in fundamental physics to test exactly the validity of quantum mechanics for very complex objects. I mean, I wrote here complex, not large, but in some way, and I think this was an argument by Deutsch, if we could build a quantum computer which is equally complex as a human brain, then we could essentially carry out this experiment. Of course, with the simulated brains, not with ourselves, but this would make this experiment feasible in this sense. But this is now the most interesting slide, and this will be the last slide, except for the conclusion slide. You can now, I mean, the theory just tells you that whatever view you have on quantum mechanics, you can kind of categorize them and see which of the assumptions is not fulfilled. And the only thing I'm saying is that you will never find a row that has 3 marked green marks in it. This cannot exist. Now you can go through all the interpretations, or these are not all, by the way, but sometimes it's maybe a bit unclear. So, for example, for many words, I put this because, as I said, versions of many words where you have branches that are stable or persistent would not satisfy this thing. You would also run into a contradiction. Whereas if you give up that, you would no longer violate that. And then there are, of course, collapse theories where it's obvious that they violate this assumption of the universal use of the quantum mechanical rules that I used. There are certain theories where I have in discussions with the people who propose these theories not yet reached a conclusion, and one of them is cubism. There are others where I had very long discussions, for example, consistent histories, where we actually arrived at the conclusion together with the people. For example, it was Rob Griffiths who was very patient in discussing that with me over email. And so this is essentially just an overview. And of course it's not very precise because Copenhagen is not even so well defined. So this should not be taken as too strict, but this just gives you a flavor. I mean, the idea is that whenever you have a precisely defined interpretation, you should be able, I mean, if it's precise, you have to be able to put the mark somewhere and the crosses somewhere.
Why Gomian mechanics violates QT?
Pardon?
Why Gomian mechanics violates?
Maybe this has a long answer. Maybe I take that to the discussion part right after the talk. But this is a very good question. Why has Gomian mechanics that? Okay, let's do that later. But as I said, I mean, now to come back to the beginning of the talk, I had some favorite interpretations. which, however, have now a cross here, and I also have my favorite assumption, which is that I don't want to give up that one. And so I'm essentially now at loss because no of the existing interpretations, the ones I'm aware of, has the good properties or survives this thought experiment in my opinion. And so essentially, yeah, I'm totally confused after that. So I don't know what to do and what to think. So that already brings me to an end. This is just, again, just a summary of what I said. So it's, the conclusion from that is that, of course, these are more precisely defined, but essentially we have three assumptions that sound reasonable and are often used in interpretations of quantum mechanics, but one of them must be wrong. The third one, I have to say, is not so often considered, and that's the problem when one wants to make such a table. That's, for example, in cubism. Cubism is often seen as a single agent here. It's just me and the world around me. Cubism doesn't say whether two users of cubism are supposed to be in any way consistent with each other. There's just no statement made about that. And that's why I had question marks about that. Okay, that brings me to the end. For those who are more interested, I refer to this thing. It's, however, quite outdated. I will, in 3 weeks, at the earliest, put a new version on the archive, which includes many changes and reflects the change of my view, which was quite dramatic from the time before I wrote this, or when I wrote this first, and that after all the discussions with very, let's say, knowledgeable people. Okay, thank you for the attention.